My name is Heng Ban. I'm a professor in mechanical and aerospace engineering at Utah State University. One specific project in my lab is a nanoscale measurement of material thermal conductivity. So it's a Department of Energy project. We're using very advanced atomic force microscope using the thermal mode in high vacuum using two tips to measure nanometer scale thermal conductivity. The system, the equipment, is probably the only one in the world. I don't think anybody else in the US has it.
So this machine is what's called an atomic force microscope. It's a pretty special machine in that you can measure surface characteristics at nanoscale measurements. What we're doing is using the ability of the machine to control a tip to bring a thermal tip close to the surface of a sample. And the goal is then to be able to measure thermal characteristics of the sample with nanoscale resolutions. So the idea with this is that we can have experimental measurements that can either verify, validate the models that we have for small scales and use that to better connect those models to the macro scale. Tools like this possibly could be the answer to be able to validate models to do that.
Yeah, spider silk is a unique material. It's a biological made of protein, a biological material. It has a very unique property. Last year, it was discovered that its thermal conductivity is the highest, as high as copper. If it's lightweight as hair, but high conductivity as copper, the immediate thinking is that you can use it for space applications, for thermal management in space. So we're doing a lot of work, a lot of research, using lasers, using atomic force microscope, and doing measurement in high vacuum, actually under cryogenic temperatures. That's for specifically for space applications.
This lab, we look at the thermal properties of spider silk, so how well it transfers heat, with both a natural silk and a synthetic silk. So we look at the natural spider silk. We also look at the synthetic silk. So this comes from the spider goats. So Dr. Randy Lewis's lab makes synthetic spider silk proteins, and they spin it into these fibers, and so we have a chance to make synthetic spider silk from goat's milk. What we do here, once we get the silk from Dr. Lewis's lab, we'll place it on these sample mounts. So there is actually a spider silk strand across each one of these. We have copper on here because thermally we want to make a heat sink, and copper is a great heat sink. So we'll put this across here, we'll cover it with gold so we can actually have electrical connection across there. And then we'll place it inside our vacuum chamber. And then we'll pull vacuum on it, and we see how quickly that heat basically moves through the fiber, and we can track that. And so the faster it goes, the more similar to copper this spider silk is.
We're working with international organizations such as university labs, the top labs in France and Belgium. And my students are working with them to develop techniques of such kind of measurement. So we have used lasers to focus down the laser spot or spots to very tiny sizes, basically 1 or 2 microns. And we use 2 lasers to do thermal measurements using what's called a thermal wave technique. And basically your eyes cannot see the size of the laser spots. And we use that to measure the grain boundaries of ceramic materials, the thermal resistance of these ceramic materials. And these information will feed into the fundamental understanding and also what's called a molecular dynamics simulation to understand the basics and the reason from the very fundamental level of the thermal conductivity or the thermal performance of materials.
Oh, so the idea is to use the laser, a modulated heating laser frequency to heat the sample to bring a sine wave heat flux to the sample, and the optical reflectivity of the sample is we change at the same frequency with the heating laser but with a phase lag. And we use another laser with a different wavelength, basically different color, to measure the optical reflectivity change, which is also the temperature change. And the phase lag between the heat source and the sample will be used to measure the thermal properties like thermal diffusivity, conductivity, and thermal effusivity. We're going to bond two materials together to make different samples and measure the thermal resistance on their interface. And we also can measure, like, simply measure the thermal properties of basically any materials. But like to measure the interface is something new, and we cannot find really, very many literatures which have been published. Like you can find. So it's pretty new.
Thermal phenomena is a very important aspect of material applications. For instance, your computers. Right now, the bottleneck actually is the thermal limitation. When you pack so many transistors in a tiny, tiny area, the heat generation is so high that it basically will destroy the chip itself. Now, how do you dissipate the heat? Well, you use better heat-conducting material to dissipate the heat. How do you develop the material? Well, you first have to understand how the material or why the material has high thermal conductivity. If you fundamentally understand that, then you can use nanostructures, you can build the materials from bottom up, atom by atom, to make a superconductive material, yet electrically insulative. So that way, you can do a much better job in terms of dissipating heat and resolving the bottleneck issue of computer chips. When I say I do mostly energy research, energy is mostly from heat, either from combustion or from light, from solar or from nuclear or from various sources or even geothermal. Now, heat is an important part of it. So how do you better insulate the heat? Or how do you better conduct the heat? How do you perform better under very high temperatures or high pressures? All these comes back to the fundamental or basic understanding of the material behavior from the atomic level. So if you understand them, you can always find ways to build a better material, a super material, to meet your needs from the thermal aspect.